Can you see my screen? Am I audible? Please respond. Am I audible?
Yes, sir. Yes, sir.
So today I will take a brief class, not much. I shall cover today. So I want to start today the reversibility of non-uniform cellular automata. We have discussed non-uniform cellular automata, in particular finite non-uniform cellular automata, and then we introduced two characterization tools, namely matrix algebra and reversibility tree. While we discuss this reversibility, then we shall use these two tools to decide or to understand reversibility of non-uniform cellular automata. Okay. So, in my discussion, we shall stick to the finite cases only. Okay. So this is I'm discussing about reversibility of finite CAs, and in our case, the CA, they are non-uniform cellular automata. So we have seen that reversibility, actually bijectivity implies reversibility, right? So reversibility is a meaning. It generally means time reversal, but means from one configuration you can move in back. Sorry, you can move to backward direction. Sorry. Hello. Okay, I'm in class. Can you call me after? Okay. So bijectivity implies reversibility, because reversibility, by reversibility we mean that we can move in backward direction. So from one configuration we can go to the its predecessor, its previous configuration. It means it's possible only if CA is bijective, right? If a CA is bijective, then it is then the CA has an inverse, right? And we have seen that from Hedler's theorem that inverse is also a CA. So from that you have understood that bijectivity implies reversibility. And for classical CAs, it's also proved that classical CA means you have a single rule and the lattice size is finite, right? So in that case, injectivity implies bijectivity. That is, if a CA is injective, it means it is always surjective. So we can say that injectivity implies bijectivity. However, in classical CA, if a CA is surjective, right, it does not always mean that it is injective. Okay, we have seen it. With example, we have seen it. Say, for example, in case of ECA rule 30, the surjective CA, but not injective. Okay, but if it is injective, then CA is surjective, hence CA is bijective. That we have seen in our previous classes where we have discussed the set theory properties, the reversibility, etc. So therefore, for classical CAs, injectivity implies reversibility. However, for finite CAs, surjectivity implies injectivity. Injectivity, in case of classical C also implies surjectivity, but specialities here is that surjectivity itself implies injectivity of RCA. So what's the meaning of surjectivity? In codomain, right, all the elements are covered, right? So in a surjective CA, codomain is set of configurations. So each configuration has a predecessor, right? It's the meaning of surjectivity. At least one predecessor it will have. Okay. So in this case, in case of finite CA, if it is surjective, then the CA is injective. Okay, that also mentioned. I guess when Kari was talking about the structural properties of CA, that is also mentioned. Take an example. So now in our discussion, we shall concentrate only on finite CAs, right? So in left hand side you have irreversible CA, and right hand side I have given an example of reversible CA. In case of irreversible CA, it is not surjective, not injective, right? You can see in the right hand side figure, it is a 4-cell CA of 165, 73, 290. In previous class also we have taken this example, right? So you can see, in the configurations there are many to one mapping, right? And there are some configurations in the CA, 4-cell CA 165, 73, 290. There are some configurations which are having no predecessor. These configurations are called non-reachable configurations. So in last class we defined this one. So there are some non-reachable configurations. What is the meaning of non-reachable? What is the meaning of non-reachable configuration? A configuration is non-reachable. It means it has no predecessor, right? So in a codomain, you'll find some configurations which are having no predecessor, right? So the CA, the right hand side CA, is not surjective CA, right? Because many to one. I mean, there are some configurations, where there are some configurations which do not have any predecessor, right? And here you can see there is also a many-to-one mapping, right? Anyway, so in this case, let us define one more term here called cyclic configurations. So in any finite CA, in fact in any CA, you'll find some configurations that form cycles. So be it surjective CA or not surjective CA, be it reversible CA or irreversible CA, you'll find some configurations which are, which form a cycle. Those configurations are called cyclic configurations. In case of reversible CA, okay, in case of reversible CA is injective as surjective. You can see the example for cell CA 90, 15, 85, now 15. This 4-cell, this 4-cell CA, you can see that the CA is, injective CA, right? And it is surjective CA. In the transition diagram, you'll find no configuration which has no predecessor. So each configuration has a predecessor, right? You can see, right? And all the configurations, they are mapped to a unique configuration. So there is no many-to-one mapping. Further, you can see all the configurations of reversible CA, they form cycles. They are in cyclic, they are cyclic configurations. All configurations, they are cyclic configurations. So this is the specialty of of finite cases. So all these things you may not find in case of classical CL. So to our case, these are equivalent. So let us go to the Jamboard uh, to tell you. I think it's clear what I said here. What I said here is clear. Still, okay. What happened? So this was my configuration, which I was discussing. So I think it is clear. Still, let me. So here, what I was saying here, I was saying you can see this configuration, this configuration, this particular configuration, you can see it has no predecessor. It has no predecessor, no predecessor, no predecessor, no predecessor. So they are non-reachable configurations. So it makes the presence of these non-reachable configurations makes the CA non-surjective, right? It makes the CA non-surjective. So it's non-surjective CA. And it is not injective also. See, why it's not injective? You can see there is, a many-to-one mapping can see. Here, this, this configuration, it has many-to-one mapping. Right? So two predecessor it is having. Similarly, this is also having two predecessor in this way. So it's interesting here. So if you have some non-reachable configurations like this, then you'll have many-to-one mapping. This you can't find, you may not find in case of classical CA. But here, if it is finite CA, so existence of non-reachable CA, non-reachable, non-reachable configuration. So if you find non-reachable configuration, configuration, if you find some non-reachable configuration, it means, what does it mean? It means, configuration with no predecessor, This implies, in case of finite CA, this is a both-way implication that configuration, there is some configuration with more than one predecessor. Right? So if there exists, I should write here, if there exists some configuration with no predecessor, it implies there exists some configuration with more than one predecessor. This is special property of finite CS. In case of infinite CS, it is not always true. For example, ECA 30. In case of ECA 30, there exists no configuration which has no predecessor. Means in ECA 30, each configuration has at least one predecessor. But in that ECA, you can find two configuration. You can find a configuration which is having more than one predecessor. Right? So this relation is true. This what I've written here. This is true only for finite CS. Okay. So, and I was talking about the cyclic configuration. So these configurations, these configurations, these are cyclic configurations. Why? See, it forms cycle from 000 to 1100. From there, I can go to this 0100, and from this one, I can come back to this 0. So it forms a cycle, right? So these configurations are cyclic configurations. So in this CA, in this diagram, you can find 1, 2, 3, this and 4, 5, 6, 6 cyclic configurations. Right? So in general, when a CA is given, a finite CA is given, you'll find some cyclic configurations, some acyclic configurations. Acyclic configurations are of two types. One is called reachable. These are reachable configurations, and this is called non-reachable configurations. Okay. So in fact, I should say in the reverse way. The configurations are of two types: reachable and non-reachable. So here, these are the non-reachable configurations, and rest are reachable. So from reachable configurations are of two types. So cyclic and acyclic. Cyclic is if a configuration lies in some cycle, then the configuration is called cyclic configuration. Right. In case of reversible CA, in case of any question?
Sir, why 110? This is reachable configuration.
Sorry.
You said non-reachable configurations are the first four configurations, right? Why this 0110? This is reachable.
No, this is not reachable. Have I said this one? This one? No, it's not reachable.
Yeah.
So I'm sorry if I said that one. So 1, 2, 3, 4, 5, 6, 7, 8. These 8 are non-reachable.
Okay.
Okay.
Then what is acyclic configuration?
Acyclic configurations, a configuration which is not cyclic, and a cyclic configuration is a configuration which which lies in a cycle. Okay. Say one. Sorry. So here you can see 00011000100. These three configurations, they form a cycle, right? So all the configurations are cyclic configuration. 1000, this forms a cycle of length 1. This is cyclic configuration, like this. It's okay.
Okay. Okay, but here there is no reachable acyclic configuration, right? In this example.
Yes, this is reachable. Say this is 1001. This is reachable. Acyclic.
Yeah, this one is
0,
but acyclic.
011 reachable but acyclic.
Okay.
Okay. So in this way. Okay. Now, in case of reversible CA, what happens? All the configurations are cyclic. Okay. So sometime we write reversible we define in this way: reversible CA. Reversible CA. If a CA is reversible, sometimes we say in this fashion: if a finite CA is reversible, if all the configurations are cyclic. So all configurations are cyclic. Okay, this is direct definition, right? So reversibility is in to be bijective, right? From that definition, I'm getting this one, right? See, let me tell you in this way that if in a finite system, in a finite system, how many configurations you are having? Suppose you have, say, A is equal to, say, D, and L is N, say. So you have N cells here. So number of configurations to the power is equal to the power N is finite number, right? So if you start from one configuration, you will go to the next one, then you will go to the next one. Now, if you keep on doing this one, after some time, you have to come back to the old configurations which you have already visited. This does not happen in case of infinite C. But since number of configurations, they are finite, so if you keep on running the system, after some time, it has to revisit some old configuration. So it means if I draw the diagram in this fashion, it has to come back at some point of, say it's coming here, right? Now, in case of reversible CA, okay, reversible CA means I have to go in backward direction, right? And reversible CA is injective. So since if it's injective, this kind of relation is not allowed. From one configuration, one configuration cannot be reached from two other configuration, from the definition of injective CA or property of injectivity. So this is not allowed. So what is allowed? So this kind of relation is allowed only from one configuration to another configuration to another. So it is reachable only from one configuration, right? This is a property of injectivity. So now if I doing this one, then, and if it is finite CA, then what is option? Option is after some time, if it has to return back to its initial configuration. Suppose this is my seed. Seed means initial configuration, where from I have started. So from this configuration, I am going to next one, then next one, then next one. So many-to-one mapping is not allowed here, and number of configuration is finite. So therefore, after some configuration, it has to come back to the the initial configuration, right? Because the system is finite. So therefore, you'll always get this kind of cycles. According to our definition of cyclic cyclic configuration, that a configuration is cyclic if it lies in cycle. So therefore here what you can say, I mean, all the configurations are cyclic, right? So from the original definition, right, we say that CA is reversible if all of its configurations are cyclic, right? You can see here, that all the configurations here, in the 4 cells CA 90, 15, 85, 15. So all the configurations there, and they are cyclic here. Okay, it is true for all reversible CA, right? So therefore, what I get, reversibility, surjectivity also implies reversibility, right? Surjectivity means you'll have no configuration which has no predecessor. So it also implies the CA is reversible. Okay. Right? Any question? Now, from from this definition, we are moving to the next topic: reversibility of linear cellular automata. So we shall use a well-known theorem of matrix algebra called invertible matrix theorem. So it has many statements. So we have taken some statements which are useful to us. When a matrix is invertible, right? What does it mean? Okay. So this very basic theorem of matrix algebra. Obviously, I shall not go to the proof of this theorem, but here I shall use this. Okay. So I shall use this invertible matrix theorem to explore reversibility of linear CS. This is my theorem. Let G be the global s to the power L to s to the power L, global transition function of a linear C, of a finite linear C, right? See, if I talk about in this discussion, if I say CA, it is a finite CA, right? Okay, and say T is its characteristic matrix, right? Then following statements are equivalent. So what are the statements here? So T is invertible, right? If G is a linear CA and T is the characteristic matrix, T is invertible, say. That is T has some inverse. Saying this, it means that determinant of T is non-zero. That is, T is non-singular, right? So 1 and 2, these are equivalent. It implies, so you can say here, say from here that if T is invertible, then determinant of T is non-zero, right? Then you can say that the linear transformation G is injective, is 1-to-1. Then you can say that linear transformation G is surjective. Just now I have said this one. So if I have matrix, I have a, if I am having a matrix, the CA is CA is finite, right? So 3 and 4 is saying that if a CA is injective, then it's surjective, and vice versa. If CA is surjective, then it's injective. And number 5 is if T into x equal to 0 has only trivial solution x equal to 0, right? So in this case, only for x equal to 0 is true, right? So these 5 statements are equivalent. So therefore, if T has inverse, then determinant of T, then T is non-singular. Or if T is non-singular, then T has an inverse, right? So this theorem, if you want to have the proof of this theorem, it's a very basic theorem of matrix algebra. You go to any book, and these proofs are available. Okay. So actually, this is the advantage of using matrix algebra. So these theorems are there. Just I have taken the result, right? Just I have taken the result. And what is the meaning of T is invertible? T has inverse, right? Inverse means it's from one configuration you can go to the previous configuration, right? It's the meaning of reversibility, right? So if T is inversible, actually the CA represented by T is reversible. That is the meaning. So how can I do this one? So take this example. Say under null boundary condition, the CA 90, 150, 90, 150 is reversible. See, in the left hand side, T is for the CA 90, 150, 90, 150, right? So you can we have discussed it. It is how can I get this T? Let me recall it again. And here I am saying it is reversible. On the other hand, 90, 150, 90, 90, it is irreversible. So recall that 90, 150 both are linear rules. So go back to the Jamboard. Okay. So what is my CA? It was 90, 150, 90, 150. For recalling, I am saying that 90, rule 90, what is this? It was like this. It was X XOR Z, right? And in case of 150, X, Y, Z, it has three arguments. It's thinking about CA, we are talking about ECS. It is X XOR Y XOR Z. So I can say that in this case, if it is a cell depends on left neighbor in case of 90 and right neighbor only because it has no dependence here. There's no Y. And in case of 150, a cell depends on itself, on left neighbor and right neighbor. Now this is my CA. What is my T matrix here? My boundary condition is null, so it is rule 90. So cell number 0, it is saying that it depends on left neighbor and right neighbor only. Left neighbor is 0, it depends on right neighbor. So no dependence on self. So here 0, here 1, because it is Z is there, right neighbor dependence is there. So 0, then 0. For the second cell is 150, it depends on cell number 1. This cell number 1, this depends on left neighbor, self and right neighbor. So I can write here like this one, 1, 0. It's 90 again. It is 0, 1, 0, 1. And it's 150. It is 0, 0, 1, 1. This is my T. I have to test if that CA is reversible or not. What it is saying? What my invertible the theorem is saying from the invertible matrix theorem. What I get, if the T is invertible or T has a reverse, if determinant T is determinant of determinant T is non-singular, it is non-zero. Okay, so then it means I have to find out this determinant of T. You find this out. It will be then 0. What will be? So 0. So first part will be 0. Then plus 1. It will be 1, 1, 0. Then 0, 0, 1. Then 0, 1, 1. Rest part is 0. I'm not writing because it is 0. It is 0. This is yes. Any query?
Hello, sir. Sir, how did you write T matrix, sir?
T matrix. How am I writing?
Yes.
So when a CA is given, when a linear CA is given, okay, from that I can get the T matrix, right? And how can I know that CA is linear? If all the rules of the CA, they are linear. That we have discussed. Okay. Now this kind of CA is called non-uniform ECA. Why? Because all the rules are ECA rules. Okay. In case of ECA rule, a rule can depend on left neighbor, self, and right neighbor. Here, there are 4 cell CAs like this one. If I draw the diagram, there are 4 cell CAs. Right? It is null boundary, so left 0, right 0. Right. So here cell 0, cell 1, cell 2, cell 3. So a cell number 1, it can depend on its left neighbor, self, and right neighbor. Sometimes a cell may not depend on all of its 3 neighbors, but may depend. So now rules are given. Now I know this rule is 90. First rule is 90. Okay. If you find the expression of this rule 90, then you'll find that rule 90 is nothing but X XOR Z. That is x plus z mod 2. This is rule 90. Okay. I can show you because I have shown in previous classes. I can show you how I'm getting so. So for rule 90, okay, let me show you. If you forget that one, say how can I get this one? 0 0 1 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So 8 possibilities are there, right? 0 1 2 3 4 5 6 7 8 possibilities are there. Were there, right?
Yes, sir.
Now in case of rule 90, it is actually 0 1 0 1 1 0 1 0. It's 90 actually. It is rule 90. So I know, so I have written. So it is rule 90. You can see here, you can check whether I have written correctly or not. So it is left neighbor is this one. This x, y, z. Okay. So omit the middle bit. So x and z. So first and last. So first, 2 bits. 0 or 0 x or 0 is 0, right? 0 x or 1 is 1. 0 x or 0 is 0. 0 x or 1 is 1. 1 x or 0 is 1. 1 x or 1 is 0. 1 x or 0 is 1. And 1 x or 1 is 0. So it actually proves that I have written correctly. Right. So from the rule also you can find this one using
Yes.
corner map. You can do this one. So this is 90 x dot z. Similarly, you can check in similar fashion that in case of 150. So in case of 150 like this 0 1 1 0 then 1 0 1. This is 150. So here you can see that if you draw the 3 bits, 0 dot 0 dot 0 is 0, 0 dot 1 is 1, 0 or 1 dot 0 is 1, 0 dot 0 dot 0 1 or 1 is 0, and so on. So here it is 150. It is like this one. So I got these two rules. Is expression. Now from this expression I can get this t. So here, what happened is x or x, y, z. Here I want to mean that x is the left neighbor, right? Here I have to say x is the right neighbor, y is the self, and z is the right. X is the left neighbor, and z is the right neighbor. So it shows that a cell actually depends cell I depends on cell number j. I put 1 in the matrix. Cell number 0. So a row represents cells. Cell number 0. It depends on itself, no, but it depends on right. So I put a 1 here. It depends on left, but since it's null boundary, 0 is here, so practically it has no dependence. So nothing is written here. It is not possible also. It's a boundary cell. So after this one, second cell. Here is 150. It depends on itself as well as left and right neighbors. Here 1 because it depends on itself and its left neighbor 1, right neighbor 1. So 1 1 1 plus 90. Second cell. Depends on itself? No. So because 90 doesn't depend on itself, 0. But depends on left neighbor as well as right neighbor. So 1 here and 1 here. Right? So here. So 1 0 1. And finally, cell number 4, 150. It depends on itself and left neighbor and right neighbor. So 1 1, but right neighbor is 0. This is null boundary condition. So 1 1. So this is the way of getting the matrix in this case. Follow one lecture that where I discussed how to get this matrix. It is said that for other permanency, how can I get that? But for this kind of CAs, binary CA, we can get T matrix in this fashion.
Okay, sir, got it.
Okay.
Thank you, sir.
So now, you can see that using T matrix, you can get the next configuration. Here we are considering configuration as a column vector. If you multiply this with a column vector, you will get another column vector. So which is the next configuration of the previous one, right? So T matrix actually is operator. Okay, sorry, it is generator who generates all the configurations, the configuration space of the linear CA. Now today I am discussing when this T is given, from that T, how can we decide that the CA is reversible, right? So invertible matrix theorem is saying that you can do that one. How? You can do it by just finding out the determinant of the matrix, right? So here, so I am, okay. So come to, so now T is this. From this T, I have to find a determinant. First part is 0, so it's no value. So then 1. So I am taking 1 and this determinant of this part, right? So this is actually equal to. So if I take 1, this 1, then it is actually, it's very simple actually. I'm just showing you, but you all know how to find determinant. Sorry, 0 1 and 1 1 plus here is again 1. For this one I'm writing here, say 0 1 0 1. So this part is, so this part is 0, so actually 1 plus 0 equal to 1. This part is 0, this part is 1. So determinant of T is 1.
Sir, it will be -1, right? 0 minus 1 into that part.
Okay, so here minus is not defined. Here minus is not defined because we are using, say, XOR operation here, na? XOR operation, modulo 2 operation, right? And actually, theoretically, our field is GF2, Gauss field 2. Okay, minus and pi plus both are equivalent actually, right? So you can think that we are using XOR, right? So no minus operation is defined here. So
in finding determinant also.
Yeah. Yes.
Okay. Okay, sir.
Okay. Yeah. So determinant of T is 1. So therefore, from the theorem we get that T is, this T is invertible. So therefore reversible. So it has inverse. T has inverse, right? So it is a reversible C. How I get this one? I get from the from that one, from the invertible matrix theorem. Similar, on the other hand, if I am given, say, so the example what I've taken, I've taken maybe 90, 150, 90, 90. Yeah, that example I've taken. So this I have taken. So here, what is the matrix? Matrix is 0 1 0 0 1 1 1 0 0 1 0 1 and finally 0 0 0 1 0. You can check it. So if you find this one, this is a determinant of T. So it will be 0. So it's no value. So 1. So 1. I'm getting what? What I'll get? So 1, 1, 0, 0. Please let me know if I commit any mistake. 0, 1, 0. This one is equal to, this is 1. This is sorry. This is 1, 0, 1, 0, 0. This is 1. Another is like, oh, here I committed a mistake. In case of 1, 0, 1, 1, 0. Okay, yeah. Is 1, 0,
Yes, sir, it is 101.
0, 1, 1, 0. And in this case, it will be 0, 1, 0, 0. Right? Am I right?
Sir, initially you took wrong, I think.
Yeah, maybe.
110, 101, 010.
110,
101, right?
110, 001. So 1 I am taking.
Okay.
001 and 010. Right? So this 1, then 0110, and for 1, 0100. Then what it will be? It is again 1. Any wrong I am doing? Any wrong I have done?
It will be -1, sir, but you said you will be considering 1, right?
So okay, so this will be again 1, no? This will
1,
be,
sir.
so then if it is 1, then I wrote wrong thing, in the slide. Right, what I have written here? 90, 150, 90, 90. It is irreversible, I have said. So if it is non-zero, then it will be reversible. Just let me check it again. One, 0, 1, 0, 0. Okay, so if it is 1, then again it is again it is reversible. So if it is 1, since it is 1, then it is again reversible. But somehow if I get it non-1, okay, so let me take an example what I can show you. It is, so let me take everything as 150. Let me check. So in this case it will be 1, this will also be 1, right? So here it will be 1, it will be 1 in this particular example. So here Yeah, in this case, yes. So yeah, in this case it will be 0. Right? Am I right? In this case, Devada, if I put here 1, if this CA, okay.
Ah,
So
yes, sir.
if this CA is like this, if my CA is 90, 150, 150, 150, then I get
Then
determinant
0, 0.
is 0. So this CA is irreversible. Irreversible. So it's a way of deciding whether a linear CA, linear finite CA is reversible or not. Okay.
So the second determinant would be 0, 1, 0, 1. The last one.
It would be 0,
0,
1.
1, 0, 1.
Yeah, 0, 1, 0, 1. Yeah, okay. 0, 1, 0, but it's 0, right? I wanted to reach to that one, that some C is reversible, right?
Yeah.
If it is 0, then it will again be 0. So it is reversible. Sorry, irreversible. So in this way. Okay. Now, let us now explore an interesting property of this reversible CA. This kind of reversible CA means we are talking about non-uniform CA, but non-uniform finite reversible CAs, right? So we get that for a reversible CA, a configuration, say configuration is X, it will return back to its original position, configuration. The configuration will be returned back. So therefore, after some evolution, from if I start from X, I'll get back X again. What does it mean? What does it mean? It means that I have started from X, then by multiplying X with T, I'm getting a new configuration. Okay. Then with that new configuration, if I again multiply that one with a T, means T square X, I'll get another configuration. Now, since it is reversible, after some time it has to come back, right? So X will be T to the power K into X for some K. So K may be 1, 2, etc. some natural number K, right? If it is so, what does it mean? It means to the power K is actually an entry matrix, right? To the power K is an entry matrix. So that we get. Now from this information, I am claiming that T square to the power K minus 1, that forms a group, another operator minus multiplication. If matrix multiplication is an operator, another that one, it forms a group. Okay, let me go back. Where is my that one? Okay. What I'm saying here? I'm saying here that see X is a configuration. My C is reversible, right? So then what does it mean? That from the X, I'll get the next configuration as say TX is my next configuration. T of X is my next configuration. So that is, so T square X. So what I get, X is the first configuration, then TX is my next configuration, T into X is my next configuration, then T square X my next configuration, and so on. Since it is reversible, and since my C is finite, after some time I'll come back to this X. So therefore, say suppose to the power k minus 1 into x is configuration, but after that to the power k into x is actually x. That I've said, here k is a any number greater than equal to a natural number greater than equal to 1. That you understand. So from this one, from this relation, it's very simple. From this I get that to the power k is equivalent to I into matrix. I am claiming here the set of operators. So here see, so t squared the operator, t is operator, obviously t matrix, t square is another operator, right? So these operators. So I, so the first one, then t squared, then to the power k, minus 1, these forms a group, right? This forms a group. What are properties of forming a group? So okay, what is the operator here? Operator is matrix multiplication. So this set of operators, right? It forms a group under matrix multiplication. So this operation is closed. So what is the four properties of what are the four properties of group? First, we show that it is closure. So closure. So it is closed. It's closed means if you multiply say to the power I into the power j. So what you will get to the power I plus j. Okay. So I plus j either in this set or outside of this set. I mean I plus j. If I plus j is I plus j is greater than k, right? If it is less than k, then obviously I to the power I plus j is in this set. It is greater than k. So if I plus j say greater than equal to k, what will happen? See, from this relation I understand if it is greater than equal to k, then what I can write? So I can write that say k plus 1. So I can write I plus j. I'm just giving an example that say it is equal to k plus 1. What is the meaning of this? Then to the power I plus j equal to the power k plus 1 equal to the power k into 1 to the power k is I. So I into t equal to t. So t is in this set. So here is a model operation is there because to the power k is I. And then if you go further, to the power k plus 1 is actually t. To the power k plus 2 is actually t square. To the power k plus 3 is actually t cube in this in this way. So therefore it follows the closure property, right? Secondly is associativity. So we know matrix multiplication is always associative. Okay, so here also matrix multiplication is associative, so it follows the associativity property. That is in other words, in this case obviously it follows. What does it mean? What does it mean? That is the I tj, right? Into tk. So okay, I write a here is equal to say ti dot tj dot tl. This is the meaning of associativity property. So I am first is bracket means I am firsting I first do this operation. Okay, and here I first do this operation. So the same meaning actually. No matter how you put this parenthesis, the result is same. So here it is associative. Okay, in general, matrix multiplication is associative, but not commutative, but it's associative matrix multiplication. Third number is existence of identity. So identity, sorry, identity. So here identity exists. Here I is the identity. Identity matrix. You can see here I. So you can multiply with any to the power I, to the power I. So you're having this identity. And fourth is inverse. So from from the invertible matrix theorem, we know if T is there, T will have that, it will have inverse, right? Now, if since T is singular, T square is also singular, and from that matrix theorem, invertible theorem, we can get that for each operator T square to the power k minus 1, each is having
non-singular, right?
Sorry, inverse. Sorry.
Non-singular.
Oh yeah, non-singular. Sorry. Thank you. So since each one is non-singular, T is non-singular, so T square will be non-singular, and so on. And from that inverse theorem, matrix inverse theorem, you get for each one, for each element of the set, each element of the set, they're having the inverse. So inverse exists, right? So in fact, inverse can be shown in the other way also. What is the meaning of inverse? So here, if you say that t to the power I, right? To the power I, and say its inverse is say say x is I should say x or no? Say A is inverse. If A is the inverse, then it is to be I. Okay. So now you can always have this A. How? Because this is actually I means to the power k, right? So if A is to the power say 2k minus I, right? Or say k minus I. Why 2k minus I? K minus I. To the power I, to the power k minus I is equal to the power k is equal to I. So inverse exists. So therefore, it's a trivial one. It's a very trivial one. So what I want to see here, that all the properties of group is followed by this set of this operators T square to the power k minus 1. Therefore, this set forms a group. So this is a group property of a reversible C. And not only group. Actually, it forms a cyclic group, right? It forms a group, obviously. It forms a group, but it forms a cyclic group. What is the property of cyclic group? That all the elements of group are generated by a generator, right? And it's a cyclic like thing. So here you can see that all the elements of this T, of the set, all the elements of set are generated by say this T, right? Say from T you can get T square, just multiplying, then T cube, and then to the power k minus 1, and then I is to the power k. So actually it forms a cyclic group, right? So a cyclic group is formed. Right? So what I want to say, what is summary? That the operator T of a linear CA, it forms a cyclic group. So sometime the reversible CA are termed as, due to this reason, they're termed as group CA. So in literature, in many cases, in many papers, you can find the group CA, the term group CA. So group CA means the reversible CA, and the term group came from this property, these properties. Okay. Now, what is the k? What is k here? What is k? Sorry. What is k? This k is actually nothing but, say this k, na? Say k is nothing but, here k is the order of the group. So a cyclic group has an order. So this is a group, cyclic group of order k. So to be ordered, to be an order, so what is the property? So that what I've said, that t to the power k into x equal to x, that I've said, and k is an order if there exists no k dash, such that so it is equal to same actually. So I should say in this fashion, that to the power k dash into x not equal to x when k dash is less than k. I mean that after k time step, I'll get back the initial configuration, not before that. So this k is called order here. Okay, and this is actually, this order actually implies, existence of an order k implies cycle length. Cycle length. Since x is in some cycle, so x is cyclic configuration, and that lies in some cycle. And if it forms the order, forms a group of order k, then the CA has a cycle of length k. So this k is also cycle length of the cellular automaton. Right? Now it's simple. Now interesting things are there, that so this okay. So this is another property. When it forms a cyclic group, then this I plus t square plus to the power k minus 1 equal to 0. If you add all the operators, it will form a 0. You prove it. It is not so difficult. It follows. Okay. So if you add all the matrices, it becomes 0. It's an interesting property, and in the next theorem also we shall use this property. Okay. So so I plus t square plus to the power k minus 1 is equal to 0. If you add, you can see also just from adding, so this power matrices. Okay, this property we shall use, huh? Okay. Now, so this is about linear CA. Now, as I've said, that matrix algebraic tool can be extended to complemented CA. So we have some interesting property for complemented CA. See, let us denote the operator as T bar. So I have not used this T bar symbol in last class, this T bar actually. So what is complemented CA? Complemented CA is CA if all of its rules is either a linear rule or complemented rule. And when a rule is called complemented, a rule is called complemented if it is a complement of some linear rule. Okay, please recall that complemented rule. And complemented CAs, they're characterized by two things. One is T matrix, and this F vector. So T and F, right? And see, so here, suppose X is my configuration, right? So how can I get that next configuration, right? How can I go to the next configuration? So I have to I have to multiply this X with T into X, then I have to XOR this the resultant column vector with the F. Note that we are concentrating now only on binary CL. What I have discussed before, they're applicable to all linear CAs, binary, non-binary, etc. But now we are concentrating on only one binary CAs, right? Because complementary CAs, they are defined, they've been defined only for binary cases. Okay, so we are concentrating on only binary case. So instead of writing plus, sometimes we'll use the XOR symbol. XOR symbol means modulo 2 addition. So now we can get this relation. Say Tx equal to T into X XOR F, right? Then T bar square is actually the next one. Now if I apply it P times, right? Then what I will have? Then what I will have? I will have that one, the next one, right? In this way, okay. So here I am defining an operator. Now, interesting point is, so I am getting a new operator called T bar. It's not a matrix actually, something different, but I'm getting a new operator. It's an interesting lemma. If this lemma says, this lemma says that if T is the T matrix, characteristic matrix of a linear CA. If T is generator of a cyclic group, that means T is reversible CA. Then T bar is also generator of another cyclic group. That is, if the CA is linear, CA is reversible, then any of its complement is also reversible. It's the meaning of this one, right? If T is reversible, then any of its complement is also reversible. So to prove this theorem, we shall use this one, the previous relation, that I plus T square, etc. That relation we shall prove. Okay, let us try to prove. So I have to go to Jamboard because proof is not here. Please, at any point of time, if you have any query, any doubt, stop me. See what I get here. So here I have written, I have defined a new operator T bar is actually nothing but actually this is for complemented CA. So my discussion only for complemented CAs and obviously complemented binary CA, right? So my discussion, I'm discussing now the complemented binary CAs only. So suppose T bar is my operator, right? How can we get how can we use T matrix or lattice algebra for this complementary CA? We have discussed that suppose T is my matrix of a linear CA. From the linear CA, I get a complementary CA, right? So okay, if you forward the case, then let me just give an example, then it will be clear. Okay, suppose just for example, I am giving you, yeah. So this CA, yeah. So this, okay, this is my CA. So 90, 150, 90, 150, 150, 150. This is my linear CA, right? And this is my T matrix. Suppose my CA is like this. If I take this CA, say that, say 150, sorry, 105 or 165, 150, 150, 150. This is a complementary CA. 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 Why complementary CA? Because this rule is a complementary rule. Because you can check that 165 XYZ, if I write in this fashion, is a rule. It is actually, how it is defined? It is complement of 90 XYZ. You can check. I am not going in detail. You can check. Just 1 minus complement of 1. Okay. So 165 is a complemented rule. So therefore, this CA is a complementary CA. So how can I characterize this complementary CA? For this, I can use this T matrix. Along with this T matrix, I need a F vector. What this F vector will contain? This is, see, first rule is my complementary rule. First rule is complementary rule, so it will be 1. Second rule is linear rule, it will be 0. Then it is linear rule, it will be 0. Then it is linear rule, it will be 0. This is the way of getting F vector. So now, so to characterize this kind of complementary CA, I need T matrix, and along with that, I need F vector. So okay, so this is the F vector, right? Sometimes we call it, its name is inversion vector, right? Now, so for such, when an F vector and T matrix is given, how can I get next configuration of a configuration X? Suppose X is my configuration, a configuration. So how can I find out its next configuration? It says you have a T matrix, so you multiply X with T, then XOR or XOR with F. If you do so, then this will give you the next configuration of X of a complementary CA, right? So that we have discussed. Now here I am defining a new operator T bar. How it works? It works in this fashion. I am saying that it is actually, I am writing its equivalent to T bar dot X. So since, but this dot is not a simple multiplication, it's an operator. So although it's looking like similar, like multiplication, but it is not multiplication. So I have defined this fashion. When I write T bar into X, it actually means this one, right? Here I mean that this T bar, it also forms, a cyclic group. It's also generator of a cyclic group under this new operator, obviously. Okay, it also forms a new group. That is, what is this implication? It means if a CA is linear if T is the characteristic matrix of a linear CA, then let me say in a different way. If a CA is reversible, then any of its complement is also reversible, right? That is, if T represents a reversible CA, then T bar also corresponds to a reversible CA. That's the meaning. So let us prove this one. Before the proof, I have derived one expression like this. So this is T, then T square X. What does it mean? Then I shall apply it twice, right? I shall apply it twice. So what is this? So this actually it means T into X XOR F. This is my new configuration. I have to multiply this with T, then XOR F. This is the meaning of this one, right? So this is actually, see, I have expanded, this is the meaning of this. So this is actually T square into X plus plus I plus T into F. So this plus is actually a XOR. Actually, I'm not writing here. This plus actually XOR. I don't mean XOR. I shall write plus. Okay. So in this way, if I expand it, say to the power, say what I've written Q, na P. P I've written. So P into X. It is equal to, if you expand systematically, you'll find this to the power P into X. This X is multiplication, matrix multiplication. Then plus I plus T squared plus to the power P minus 1, right? Into F, right? Just a minute. Okay. Now whether T bar, okay, it forms a cyclic group or not, it means, it is sufficient to prove that, if I want to prove that T bar, it forms a cyclic group, it is sufficient to prove that. So I plus T bar, so to the power, say Q minus 1 is equal to 0. The relation I have shown it before for cyclic group, it is followed. And this one, this I shall show, other it is equal to I. Okay, I claim that, so that if I want to show that T bar it forms cyclic group, I shall show here only these two things. That after this means T for there exists some Q. It means there exists some Q. Okay, there exists some Q such that to the T bar Q equal to I. Okay, it returns back in the initial kind of position. It is I, and the summation is equal to 0. Okay, this is a property of cyclic group that we have discussed. So we shall show that when T only forms a cyclic group, then also the new operator T bar, it will for I mean, that will follow this relation, right? Now, try to find out the next configuration in this fashion. Here, now we are we shall find out this one. Just let me just write down. So actually, this means XOR, huh? To the power q minus 1 bar q minus 1 x. Find it out and see what we can get out of this. So actually, this is actually x I into xx plus t bar into x plus into x plus t bar q minus 1 into x. Now expand them. Okay, this is equal to, what is this? How can I write it? I can write it. So it is actually tx plus f. This is plus t square. So no, ultimately I know the property of t. So from this t bar, I have to come back this t. So t square x plus I plus t into f, right? Right, yes. In this way. And what it will be? To the power q minus 1 x plus I plus t plus etc. to the power q minus 2 f, right? It will be f that I'll get here. Okay, now rearrange them. So how I'll rearrange it? So in one side t and other side in f, then what will get here? Say x. So tx plus t square x plus dot 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 t q minus x is one side, and in other side this part. Okay, how can I write? I just let me write it first. I plus t just I plus t plus I plus t plus to the power q minus 2 into f. Okay, that I can get, right? That much I can get. Yeah, q minus 2. Then what will happen? Now consider, just considering I'm here. So what I have to show? I have to show there exists a q. Just I'm considering q equal to just 2k. Okay. I'm just considering q equal to 2k, and recall that I have proved it, I have shown it that I plus t square plus to the power k minus 1 is equal to 0, right? When t forms a cyclic group, right? So consider this one and put this one, this value. Then what I'll get? So here q equal to 2k, right? Q equal to be q will be 2k, right? And then what I'll get, will get like this. This is, if this is, what will happen here? So if I take x as what will be there here? So I should write here, I'll get just what will be here if I put it in that part. I'll have this part will be 0, right? So if I do it one, then I'll get it. Say so let me put it first, then I'll see what I'm getting. So here I am getting here I plus t square plus t to the power 2k, right? Sorry, it will be t to the power 2k, q is 2k, 2k minus 1, right? This will be 2k into x, and here plus I plus t plus dot I plus t to the power 2k minus 2 into f. Okay, so okay, that will be first bracket, then this one. So I am putting here 0. So what will happen? What will happen? To the power k minus 1 0. So here up to this, the one term is to the power k minus 1. Here one term is, so let me go to the next part. So what will be here? So it will be like this, that I plus t plus to the power k minus 1 plus to the power k, right? Then to the power k plus 1 plus dot to the power 2k minus 1 into x. Let me first delete this part. So this part is 0. This part is 0, right? Right. So and here, so this is actually equal to, so if it is 0, then I can take, so 0 plus I can take to the power as common. So then what I'll get I plus t plus to the power k minus 1, right, into x. Yeah, this part is again 0. So this part is 0. So total part, first part vanishes, right? 0 plus 0, this part vanishes, right? So first part of this one, so this is 0. This part is 0. So only this part remains. Okay. So only this part remains. So what is that part? So I'm writing here directly. Just I know since it's 0. Any query? So this is actually I. Then then equal to I plus t. What was that? I plus t, and then it was I plus t plus to the power 2k minus 2. 2k minus 2. Okay, into f. No, it was f was there, no? Just a sec. Just a sec. Just a sec. Should remove it. Okay. So what was this? Was that it was if was there? Okay, it was f into, it was multiplied by f, right? It was multiplied by f. Okay. Well, I shall deal with the f with later. So first, then put this, cause this one. Then I get this one. Then let me simplify it first. Let me simplify it first. Then I shall, I shall then multiply the f with later. Now, in the similar fashion, this was my expression. Okay, let me go to the next part because it will take much space. Then I plus t, then dot I plus t square plus dot. Sorry. Plus to the power 2k minus 2. Okay. So what I want to put I plus t plus to the power k minus 1 is 0. So that is my intention actually. So let me expand it further. So what I'll do, I'll just t plus, here one term will be there, like I plus t plus dot plus plus to the power k minus 1 will be there, one term. Then I'll get another term, I plus t plus dot plus to the power k, right? Again plus, again the rest part, this part will come here. Then t plus dot to the power 2k minus 2, right? Now this part is again 0. This part is again 0. That I have assumed. I mean, that I know. because I have assumed as T, it forms cyclic group. Then I plus T plus dot plus 0. I'll get a 0 here. Then here what I'll get? Again, this part, if it is to the power, here to the power k minus 1 is there, right? K to the power k minus 1 is there, that will be 0. So only to the power k will remain, right? Then again plus to the power k, right? So in this way, here it is to the power k. So if I repeat this one, the next part will be to the power k plus to the power k plus 1, as it will continue. Oh, here, sorry, here will be dot will be there. Then I plus T plus dot plus to the power 2k minus 2, right? That will get, right? Oh no, sorry. Why have I written? So because I am replacing everything here, so I should replace it here. So same thing, it will be like to the power k. It will start from to the power k, because previous part they will become 0 plus dot plus to the power 2k minus 2. Yeah, right. Now I'm done actually. So this is I plus T plus dot. Okay, I'm keeping 0 here. Okay, because I don't want to reduce the number of terms, so I'm keeping 0 here. This is equal to I, right? Here I can take to the power k as common, then I plus T, and then for the next term I can take to the power k as common. The same thing will happen, I plus T plus T square, and this will continue. And here what will get to the power k, if I take it to the k as common, then I plus T plus T square, etc. And to the power k minus 2 it will be to the power k minus 2, right? I've taken a k as common, and they all are I, right? So these are to the power k is I. So therefore what I get, I plus T plus dot plus 0 plus I plus, this is actually to the power k is I, so I plus T plus dot plus I plus T plus dot plus to the power k minus 2. So this is the first term, right? This is the, this is the k minus 1 term in this way. Now you see I repeated twice. Okay, I plus 1, I plus T, I plus T. I plus T plus T square, you'll get here I plus T square, right? And finally, before 0, all the terms, it was actually this term was there. Before 0, I have expanded here I plus T plus to the power k minus 1, but before that, what are the term? I plus T plus to the power k minus 2. So this term actually was here, right? So each term repeated twice, I plus I. So our binary CA, so the operation is modulo 2 operation, or XOR we are doing here, right? So I XOR I, X XOR X. What is output? Always 0. So I XOR I is 0. 1 plus T XOR 1 plus T. sorry, 1 not I plus t is 0. So we are always doing modulo 2 operation. So as a result, we get 0. Right? We get to 0. So what I finally get, come back to this place here. So what I come back, what I finally get, this part is 0. This part is already 0, very simple way it is 0. And this part is also 0. So 0 into f is 0. Right? It's null matrix 0 into f is 0. So therefore what I get? I get that there exists a Q. What am I supposed to prove here? I have to prove that there exists a Q such that this is 0 that I am supposed to prove. So I have shown here that there exists a Q for which this is equal to 0. So first part is done. First part is done. So there exists a Q. Okay, it may not work for all Q, but the point is you have to show that there exists a Q. So we have shown that there exists a Q for which this is equal to 0. Right? So first part is done. Okay. Is it okay or no? Now for the second part, I have to show that, what I have to show? I have to show that for the same Q, so to the power Q is equal to I. So what was my consideration? Q equal to 2k. So I have to show that it is 2k equal to I. Right? That I have to show. Okay. Let's start. So here what I'll do, 2k into x for any configuration x. Let me expand it. What will happen? So this 2k into x plus, let me repeat it again, plus means XOR here. So I plus t plus t square plus to the power 2k minus 1 to f that I get from the definition. To the power 2k, to the power k is, to the power k is I, no? To the power k, to the power k is I, that you know. Okay, this k is the previous k. So so here if it is so, then is I into k, I is the random matrix, and here for the previous time expand it, so t dot to the power k minus 1 plus to the power k plus dot 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 plus to the power 2k minus 1 to f equal to x plus this part is 0. So what I take, this part is 0, then I can take common t to the power k from here, take this as common, then I plus t plus to the power k minus 1 into f. So again what I get, x, this part is again 0, this part is I. So actually this, since this is 0, then I need to body, so everything is 0. So is equal to 0 is equal to x, right? So what I get, so to the power 2k. So what I get here? What I get that p dash q into x equal to x, right? So from this, I write that, yeah, to the power q is equal to I. It's same as actually it's equivalent to, it's while I'm operating using to the power q over on x, then I'm getting x. So the same as operating antimatrix on this x. Okay. So so both the part we get. So really q is equal to I. Hence the proof. Okay. So therefore, so result is hence the proof. So result is when T is cyclic group, T dash also forms a cyclic group. It forms a cyclic group, right? So lemma, what the lemma is saying. I don't know whether you're tired now. What is the time now? So I'll take not much time. Oh, it is 11. It is 1. So it's lemma. Lemma is saying, the lemma says that if a linear CA is linear CA is reversible, then any of its complement means complement, see, and to mean complement is also reversible. That is the meaning of this. So see, I have taken, why have I written any of the C, any of its complement? Because I have taken arbitrary f. Okay, I didn't put restriction on the f vector, on the inversion vector. So I have taken arbitrary f. So it's, I mean, any of its complement is also reversible. Okay. Now the last part of today's class. That's also important. Lemma says that if CA is linear CA is reversible, then its complement is also reversible. But the opposite one. The last one is so next is theorem actually. A complemented CA is reversible if and only if its linear counterpart is reversible. This is my last topic. We have to prove this theorem also. So proof is also not so big. So last theorem is a complemented. This lemma says the one way. If the linear CA is reversible, then its complement is reversible. But theorem is saying a complement is reversible if and only if its linear counterpart is reversible. Right. So now we shall prove this theorem. So already this lemma the lemma have proved the sufficiency, right? So what are the lemmas? What is theorem is saying? theorem is saying a complemented CA is reversible if and only if its linear counterpart, I mean the corresponding linear C actually, is reversible. Is reversible. Reverse SIBLE. So if and only it means both way, sufficiency, necessity part and sufficiency part. So first one way is that if linear C is reversible, then complementary is reversible, which you have proved. So one is, okay, if linear CA is reversible, then complemented CA, I mean corresponding complemented CA is also reversible. One word, so you assume that linear is reversible, then show that complementary is reversible, which we have already proved. That's a lemma, right? That part we have to prove. But the other part I have to prove that assume that complementary CA is reversible. Now assume that. So next part, the other part I have to prove. The necessary part. Assume that complemented CA is reversible. So I have to, what I have to show that? I have to show that T is reversible. Now, if if you consider the complementary C is reversible, then what will have for the complementary C is reversible? Just now we have proved. I shall use again this relation that we have shown that T plus T bar square for some Q actually is equal to 0. That is the property of, it forms cyclic loop and so it's reversible. So if I assume that complementary C is reversible, then this property is followed. And at the same time, it also follows that T bar Q equal to I. Right? From this one, I have to, I have to prove the reverse one, that that T also, the T, this is given, the T falls also, T also is generator of a cyclic group. That is, from this one I have to show that I plus T square plus P, any number P is equal to 0, and there exists a P is 0, and to the power P is I. So that I have to show here. The reverse one. Right. Okay. Now, what was my t dash? Just I shall use a trick here. Say t bar. What are the t bar x? Recall that I have t bar x is like this. T of x plus f, right? So here operator t bar is expressed in terms of operator t and f, right? Now here question is, can I express t in terms of t bar? Yeah, it's possible. So here, if I do this one, see, if I write in this way, say t bar x or f. What is this? This is actually tx plus f, right? Equal to tx. Sorry, equal to tx. Right? So therefore, just look this to one. Here, t bar x is t bar is expressed in terms of t and f. Here similarly, t I can express this t in terms of t bar and f. So what I get from here, the tx is nothing but similar type of same thing actually. I mean similar type of thing plus f. Just just roll of t and t bar, that position has been changed, right? If you look this one and this one, similar one, here t bar then t, here t then t bar. So from this, what I get, say p x is nothing but t to the power k, sorry, why k, p x plus the same thing, the t plus I can expand this one. That should I show it? No. Plus p minus 1 f. So from this one, okay. So from this, if I get this is the tx equal to t bar x plus f. So t square x will be t bar x plus I plus t bar into f. From this one, if I expand it, if you generalize it for p, so for p greater than equal to 1, okay, so I can write this one, I can get this one. If you are convinced up to this one, then we are done, right? If you are convinced, so that is what I am saying here, that in the proof of lemma, what we have done, we have expressed t bar in terms of t, in terms of t and f. Now here I am saying that, t bar x, t bar, sorry, t can be expressed in terms of t bar and f, right? So here to the power px is represented to the in the terms of t bar and f. Just roll off the bar and t they have connection, right? So what is done? So we now, since they are same, we just roll of them, t and t word they have changed, and now we can put the argument of lemma 1 to show the reversible. Okay, what what I have shown in the lemma? Lemma I have shown, it was given I plus t square to the power, oh, sorry, it will be -1, sorry, -1. In case of proof of lemma 1, this part was given 1 plus t square plus to the power k minus 1 equal to 0. From that we have proved that I plus t bar square and t bar to the power minus 1 equal to 0, and that part I have proved. Now I have shown that in the similar fashion, p can be expressed, in terms of t bar. So therefore, if I change the the positions of t and t bar, then following the similar argument, we can show this proof. Okay. Therefore, if it is given, if this part is given from this one, we get that I plus t square to the power p minus 1 equal to 0 and to the power p equal to I for some p. Right? Hence the proof. Hence the proof. Okay. So what I get, I get this one plus t plus to the power, p minus 1 to the power p minus 1 equal to 0. And similarly, we can show that to the power, p equal to I. So hence proof. Hence proof. Okay. So therefore, when a linear space CA is reversible, when it's reversible, and if a combinator is reversible, then also its linear counterpart is reversible. Yes.
Their orders will be same.
No. Not same. Not same. I mean, see, we have the mentioned here order, no?
Oh, here you are saying t to the power t bar to the power p x equals to I, but t to the power p I equals to I. That means order is p here.
No. Sorry. Thank you for pointing out this. Yeah, here I've written P and Q. Okay. So yeah, actually here what is the actually this is the statement actually. So if it is given, if Q is given, if Q is given, okay, this Q is given, this is given, then there exists a P. Right, this is the point. They may not be same, they are not necessarily same. Right. And in the proof you have seen that how I proved. I consider K equal to Q equal to 2K. Right. In the proof, what I have done in the proof of lemma.
Sir, what if it is not in 2K plus 1 or something like that?
Sorry.
What if it is not 2K? You are considered. You have considered this 2K.
Then I mean, what is the point? There exists a I mean Q.
Yeah.
So I have shown that for this it works. Obviously, for all it will not work. It cannot work. Right? It has some order. Right? Here, if it is K equal to K, then I'm not saying it order, but if I do the summation, then it will be 0, and to the power Q, I mean T bar to the power Q will be I. That is my point. But I am silent about order, right? If you ask me what is the order, is Q equal to 2K always? Is the Q the order? That I have not said. That I have not said.
Okay, so it is not the necessary relation.
No. And practically, you will see that in many cases, the order are same, but not all. There are exceptions when order gets, orders are different. I mean, the cycle order actually refers to cycles, na? Cycle, number of cycles. I mean, cycles, length of cycle, right?
Yeah.
Length of cycle means number of cycles also they are related. You'll see that, in many cases they're same, but not all cases. There are some cases where order changes.
Okay. Okay. Thank you.
Is the proof of theorem is okay? So actually, lemma is proof of lemma is the basic one. Okay, from the lemma, I can get a sufficiency proof. I get from the lemma. Necessity the proof, that part also I get from the lemma. How I get? So actually, here I have shown that. See, T bar. Yeah, T bar and T, their role are interchangeable. Their places are interchangeable. So the rationale what I put in case of proof of lemma, that is equally applicable here. Right. So I'm proved it. I've not shown it especially. Right? Yes. So I shall give an example. You can see that you can see that you can check that reversibility. If you plot the transition diagram of any complicated CA, then you'll see that if the linear counterpart is reversible, then it's also reversible. Right? That you can see. So therefore, what we get? Beat linear CA, beat complemented CA. You find the matrix, and once you have the matrix, find its determinant. If it is non-zero, it is reversible. Otherwise, irreversible. That's all. So therefore, deciding reversibility, the F vector, the inversion vector, has no rule. That's all.